Greetings, welcome to lecture number 38 on basic circuit theory. I am Razavi. Today we will begin to look at a new concept, namely the operational amplifier, also known as the op-amp. Op-amps play a critical role in most of electronics that we have today, in all devices, and a detailed knowledge of their operation is necessary. In this basic circuit course, we'll have a very simple treatment of the subject, but once we go to electronic circuit courses, such as my videos on electronics 1 and 2, we delve into op-amps more extensively. But before we go there, let's just take a look at something we covered last time, and I just wanted to emphasize the procedure that we followed and just make an additional remark. Remember that we said sometimes we end up with a differential equation that has an impulse on the right-hand side. And the procedure that we thought of was we create a new equation by changing this delta to u and then changing this y to z. Now we go ahead and solve this equation. We know how to do that. For example, if it's an overdamped response, we write it as a1 e to the s1t plus a2 e to the s2t, except that at time infinity, this z is not 0, because these two derivatives are 0, and z comes out to be 1 over gamma. So we have to add that in here so that we have a complete solution for z of t. Okay, and then we said, once we have z of t, that would be actually, if we take this derivative, that will give us y, the y that we were looking for. And after we find the expression for y, by taking the derivative of this, we go ahead and enforce the initial conditions to find a1 and a2. Now, one key note here is that because we have a u of t here, depending on the overall system, but it could be that we have a u of t, meaning that z of t was 0 before time 0. When we take the derivative of z, we have to be careful about this derivative times this. That derivative would be delta, and then we have to see what this is. But we can also predict that there should be no impulse in this derivative. Why? Because if there's an impulse in y of t, then the second derivative will have a doublet, and so on. So remember that we said that's not possible before. If you have an impulse on this side, this cannot have an impulse, this cannot have an impulse, only this must have an impulse, right? So from that, we can just work back and decide that as I take the derivative of z, I don't have to worry about the derivative of u times this. All right? Okay, so let's go back. Let's continue with today's lecture and today's study. So today, I'm going to get my pen here. Today we're going to talk about some basic amplifier concepts to prepare us for understanding what an operational amplifier is. All right, so basic amplifier concepts. All right, well, we know how to conceptually build an amplifier. So my voice is going to this microphone, and this microphone has an amplifier attached to it. So how does that work? So here's a symbol for the microphone. So we say mic. The microphone generates a voltage between these two wires that has some shape like this as a function of time. So we call this a V mic, and that's the voltage difference between these two. And I want to amplify this. So if you remember from dependent voltage sources, one possibility is to do this. We bring this here, we bring this here. We place a voltage dependent source here, a dependent voltage source here. And we say this voltage, for example, will be 10 times the microphone voltage. The microphone voltage is right between these two wires, right? And this will be sort of our common ground. And this amplifier generates an output which is equal to 10 times the microphone signal. Conceptually, we can do this, right? As I said, we cannot really buy a dependent voltage source, but we can make a circuit that sort of behaves like a dependent voltage source. In other words, this is the model of an amplifier that we can use in circuit analysis. The actual amplifier will be much more complex. All right, so this is an amplifier, right? It takes a microphone signal, it multiplies it by 10. That's what we would call amplification. So this Vout will have the same shape as that one, except that it's taller by a factor of 10. So this will be like this as a function of time. Okay, so that's a very simple picture that we create for an amplifier. I would like to make two notes about this before we go to something more interesting. So, some notes. So number one, the factor by which we multiply this voltage to get this voltage, this 10, is called the voltage gain of the circuit. So voltage gain we often denote that by A or A0. And that's really, how do I find the voltage gain of an amplifier? I take this swing, whatever it is, divided by this swing. That will be the voltage gain. So we say output divided by the input. Okay, so that's the voltage gain of the circuit. An amplifier may have a voltage gain of 5 or 10 or 100, depending on the application. All right, the second point is that if we sit here and we think of this, we can try to create a simplified picture that looks like this. So that's our input. So we say input. This is our output. Output. And what I've done is I have placed this whole thing inside this rectangle. This rectangle is a symbol we use for amplifiers. So this amplifier has an input. Of course, the input is the voltage. The voltage always is measured between 2 points. So the actual voltage is between these 2 points coming from the microphone. It goes in here. There's a common ground here. This voltage-dependent voltage source is right in here. And the output is also a voltage measured with respect to ground, just like here. So this is just a simplified picture of the actual circuit that I drew up here. All right? Okay, maybe I make one more note, even though I said only two. So here's one more note, third note. The third note is that if I sit here, I see that this line that's going to this amplifier, or this amplifier, has no current in it, right? Because it doesn't connect to anything. So we say the amplifier has a 0 input current. So we say amplifier has a 0 input current. Now that seems rather obvious and trivial, but we will see later that having this property actually greatly simplifies our analysis of more complex situations. Okay, so we got all of these here. Let's go ahead and look at op-amps. So here we saw that this amplifier takes an input voltage, right, between these two with respect to the ground and gives us an output voltage. An op-amp is a little different. An op-amp takes two input voltages, and then generates one output voltage. That's strange, but it's very interesting and very useful. So let's construct an op-amp. So here's an operational amplifier. So the symbol is like this. We have a rectangle, but we have two inputs, not one. We still have our common ground, our reference point, and we have an input which we call V in 1, You have another one which we call V in 2. Both of these are measured with respect to ground. So here, remember, there was a voltage here, this microphone from here to ground. Imagine that there's another microphone, and that has another voltage with respect to ground, and that's going, for example, here. And then we place a positive and a negative sign here. These do play a critical role in what the circuit will do. So we have to remember that there's a positive here, there's a negative here. So one input goes to this positive input, one input goes to this negative input. And the output is still here, just like the simple case. So this is the output. And what it really means is that there is a voltage between these 2 points, V out, right? And of course, this is our common ground. So we have to wrap our head around this new structure. This is more intuitive because the microphone signal just goes right in and the amplified output just comes right out. In this case, the situation is different. So of course, you have a bunch of questions right now. First of all, why do we have 2 inputs? And second, how are these related? The output is a function of what? Here, the output was just 10 times the input, or A0 times the input. What can we say there? So all of these questions have to be answered as we go along. Okay, so what the op-amp does is it generates an output voltage, V out, that is proportional to V in 1 minus V in 2. So it doesn't care about V in 1 itself. It doesn't care about V in 2 itself. It just looks at the difference between the two and amplifies that difference by some gain, by some factor. So the op-amp does this. The op-amp says, I'm going to take the difference between them, between the 2 inputs, V in 1 and V in 2, and I multiply that by my voltage gain, A0. How much is the voltage gain? It depends on the op-amp. Could be 100, 1,000, 100,000, some numbers. All right, so still this is called the voltage gain because that's how much we amplify things by. And the key is that the output is equal to the voltage gain times the difference between V in 1 and V in 2. So we don't really care how much V in 1 is or how much V in 2 is. We just care about the difference between them. Now, why is that a big deal? Well, we'll see. As we develop circuits that use op-amps, we'll see that this property is extremely useful. All right, so that's our basic op-amp structure. Now, for circuit analysis, what do? I have a rectangle, a triangle here. I don't know how to deal with this triangle, just as I don't know how to deal with this triangle. Now, this one had an equivalent circuit like this that I can use in analysis. How about that one? Well, let's try to construct something like this for the op-amp. What should it look like? Well, it should be easy, right? So here's what it looks like. I have 2 inputs, V in 1. Actually, let me try to do that on this side. So I have 2 inputs, V in 1 and V in 2. They're just sitting here, applied to these wires. I have my ground. And then I have a dependent source, dependent voltage source, whose value is given by the difference between these two times the factor, times A0. So this guy always monitors the difference between these two and generates A0 times V in 1 minus V in 2. And it delivers this voltage to the output. So this whole thing is an equivalent circuit for this, right? For that triangle. So anytime we see that triangle in a big circuit, in our mind, we can replace it with a dependent voltage source that says, let's look at the difference between these two and multiply it by a factor of A0. Okay, so that is the model of the op-amp, if you will. And still, of course, we don't quite know what's going on. Why do we have 2 inputs? What's the point of this equivalent circuit and these things? But we just take our time and gradually build up these concepts. All right, so now that I have the model of the op-amp, I can observe a few points. So the voltage gain is A0, just like before. The amplifier has a 0 input current. Here is the same thing. You see this doesn't go anywhere, and this doesn't go anywhere. So we say op-amp has a 0 input currents, to emphasize that there are two inputs and neither of them has any current drawing from anywhere. At this point, again, this doesn't seem like particularly interesting, but we'll see that it becomes very useful later. Okay, so we have this creature, this little circuit that has apparently some amplification because there's A0, right? And we just have to see how this can be used. But it is helpful to try to understand the behavior of the circuit under two very special conditions. Okay, so here's the study that we will perform. So I'm going to configure the circuit in two different forms and then try to see what it does. So here's one form. I take the op-amp and I connect this input, which we call V in 2, to ground, to 0. And I give this guy an input voltage source to ground. So we call this V in 1. And this is our V out. Is that okay? So one of the inputs, V in 2, is set to 0, and the other one has a value. And what I'm going to do is now I'm going to change this value, sweep this value, and try to plot V out as a function of V in 1. All right? So what does that look like? Well, it's simple, right? We go back to this equation here, and we say V in 2 is set to 0, so that's gone. And V out is just A0 times V in 1. So A0 times V in 1, right? So V out is just equal to A0 times V in 1. So we can plot that, right? That's pretty quick. So V out as a function of V in 1 is just a straight line with a slope of A0. Okay, so I just applied a variable voltage to this input. I changed it from minus infinity to plus infinity, and I see that V out just follows it as a straight line with a slope of A0. So the slope of this function that we plotted here happens to be the gain of the amplifier. All right, so that's fine, right? Okay, so can I predict what happens if this is a sinusoid? What do I get here? So let's go ahead and try to predict that. So if this waveform here is a sine wave like this, what do I get here? It's just A0 times that sine wave. So it's just a taller sine wave. So this will be a taller sine wave. Okay, so far so good? All right. Okay, now we go to the right-hand side and try to repeat the study, but this time we will assume that V in 1 is set to 0 and V in 2 is driven by a voltage source. I want to see if there's any difference in the behavior of the op-amp as far as its output voltage is concerned. Okay, so let's go ahead and do that. So in this case, I have my op-amp again, and the plus input, or V in 1, is set to 0. I just draw a ground here, meaning it's set to 0. And then this one has an input voltage connected to it, which we call V in 2. And of course, these are all ground, and we are interested in this output voltage, V out. All right? So all I've done is V in 1 is set to 0, V in 2 is driven by a voltage source. And again, I'm varying V in 2, I'm sweeping this value from minus infinity to plus infinity, and I want to plot V out as a function of V in 2. So how much is that? You go back to that equation, V in 1 is 0, so V out is just A0 times minus V in 2. So the plot is pretty straightforward. You can see that now. It looks like this. So V out as a function of a V in 2. V in 2 looks like this, right? This has a negative slope. So the slope is minus A0. So far so good? Okay. Now what happens if V in 2 is a sinusoid, like the previous case? Okay, so let's go ahead and do that and see what we get. So here comes the key point behind this study. V in 2 is a sinusoid. Here's a sinusoid. What does the output look like? The output is taller because we have amplified it by a factor of A0, but there's a negative sign here. So what does that mean? It means that the output is flipped upside down. So this output will be a sinusoid. It will be taller, but it's also flipped. So it looks like this. So if you have a positive cycle here, because I'm multiplying by minus A0, it becomes a negative cycle, and vice versa. So that is the output that we see here. So let's eyeball these results for a moment and see what's going on. So in summary, this is what's happening. If I make V in 2 0 and apply a signal to V in 1, I get amplification by factor of A0, and I don't flip it upside down because the gain is positive, right? On the other hand, if I ground a V in 1, meaning V in 1 is 0, the one that goes to the positive input, and I apply sinusoid V in 2 to the negative input, then yes, it's amplified by a factor of A0, but it also flipped upside down because it is multiplied by a negative number. All right? Okay, so in this spirit, we will have some particular names for these two inputs of the op-amp, because obviously these two inputs are different. They behave differently. We cannot just swap them. So they deserve their own names. So we're going to call this input the non-inverting input. Non-inverting. Why? Because when I applied the sinusoid, it did not invert it, did not flip it upside down. So we call it non-inverting. This one, on the other hand, is called the inverting input. Inverting input. Why? Because when I applied my signal only to this guy, as you can see here, it did flip it upside down. So it inverted it in addition to amplifying it. So we call that the inverting input of the op-amp. It's just a bunch of names that we have to remember as we go along so that we can discuss these efficiently. All right, so that's the one study that we had to do just to understand how an op-amp operates. Now, let's talk about another important property that comes about. So far, we have said that the op-amp has zero input currents, right? Now, there's another property that we're going to talk about that is extremely useful, and that property will be that in a good circuit design, these two input voltages are always close to each other. That's very strange, but we'll see why, and then we'll get used to it, okay? So let's go to the next page and see what this is all about. All right, so we start from here. Okay, so we say observation. So we say op-amps typically have a high gain. And when we say gain, we always mean voltage gain, A0. So for example, it could be 1,000 to maybe 100,000. It depends. If you buy an off-the-shelf op amp, it looks like, I have to be careful with my comma here. If you buy an off-the-shelf op amp, it can be, it can have a gain as much as 100,000 or lower, depending on what it is. Okay. Now, because the gain of the op amp is so high, it allows us to make some simple approximations in the analysis of the circuits that use op amps. And that's the key behind what we're going to follow here. Okay, so in that spirit, I'm going to just show you a simple example and see what we have here. So starting from here, right? Here's an op amp, and so I have a V in 1 and V in 2. And here's V out. You see, I didn't even bother to draw the ground anymore, because I know, yes, there's a ground. These are all measured with respect to ground, and this has a dependent source in here that's connected to ground, right? But we just don't bother with that. Okay, so suppose V in 1 minus V in 2 is 1 millivolt. And suppose that the gain of the op amp is 1,000. So how much is V out? Okay, V out is 1,000 times V in 1 minus V in 2. So that says that V out is 1,000 times 1 millivolt. That's 1 volt. That's fine. That seems okay. There's nothing bad about this result, right? Okay. How about if V in 1 minus V in 2 is 10 millivolts? All right, so then V out is 10 volts. That might be possible. That's okay. But let's continue. How about if V in 1 minus V in 2 is 100 millivolts? Then what happens? Then V out has to be 100 volts. So one can get electrocuted by touching the output of the op amp. Is that possible? No, that's not possible. Why not? Well, the op amp runs from a battery. So typically we draw the battery like this. It needs a power supply, right? It's an amplifier, it needs a power supply. So there's a power supply here. So this is the power supply that provides the energy, so to speak, that the op amp needs to perform this amplification. Okay, so the power supply of an op amp is typically no more than 10 volts or so, maybe 20 volts. The power supply of a typical op amp is never in the range of 100 volts or something. So here's the situation. I am asking the op amp to generate 100 volts, but the op amp says my power supply, the maximum voltage I have available to me, is only, let's say, 10 volts or 20 volts. So the op amp simply cannot generate 100 volts because its available supply range is, let's say, 10 volts or 20 volts. All right? So what does the op amp do? The op amp output saturates. And what that means is that the op amp output can never reach 100 volts. It just gets stuck somewhere, let's say around 10 volts, and it cannot go any higher. So this is the key concept that we need to understand. So we say op amp output saturates. And what that means is that it cannot exceed its power supply voltage. So if the power supply voltage is 10 volts, that's the maximum that the op amp can deliver. So if we give it an input difference of 100 millivolts. He says, sorry, I cannot give you 100 volts, I just give you 10 volts. So obviously the op amp is not working properly anymore, right? Because in response to this much, it's not multiplying it by A0, A0 being 1000. Okay, so we say op amp behaves badly. So we never want the op amp, we almost never want the op amp output to saturate, and so certainly we want to avoid this condition. All right, so let's work back and see what's happening here. The op amp says, I cannot give you 100 volts. I can give you maybe 10 volts because of my power supply limitation. And if the op amp is to give us 10 volts and not saturate, the only possibility is for the input difference to be only 10 millivolts, right? As an example, right? If the input is more than 10 millivolts, this output wants to be more than 10 volts. The op amp says, sorry, cannot do it. The op amp goes bad. So in a well-designed op amp circuit, meaning if the op amp is embedded in some circuit overall and everything is designed well, V in 1 and V in 2 are pretty close to each other. All right? Because if they're not close to each other, if the difference is large, something like this, we have a problem. The op amp goes bad. The op amp saturates. So we're going to articulate this as follows. So we say, in a well-designed circuit, V in 1 minus V in 2 is small. Now, the term small has to be quantified. We don't worry about it in this course. But so let's say some millivolts or something in that range. Okay? So this is a key concept that allows us to simplify the analysis of circuits that use op amps. And that's our first reaction anytime we see an op amp circuit. If I see an op amp, I automatically assume that the difference between its two inputs is small. All right? Presumably, the overall circuit is designed well, so we have to have that condition available. All right? So we'll see why this assumption is so useful in analyzing circuits. Okay, so this brings us to what we call the ideal op amp. And that means if you were to design the best op amp in the world, what would you like to have? So if we want to design an ideal op amp, here are the conditions. So condition number 1, no input currents. We saw that, right? We said that the two input wires are going into here. They're not connected to anything. There are no currents flowing here. So that's a nice little condition. And then the second condition, which is actually more important than this one, is that V in 1 is approximately equal to V in 2. Right? In fact, in some textbooks you might see that they say V in 1 is equal to V in 2. But I'm always careful about this. I never say equal, I say approximately equal. Because there could be confusion later. So V in 1 is approximately equal to V in 2. Why? Because we said the difference is small. If the difference is small, they're close to each other, right? So that's the basic condition that we have here. Okay, so this is very strange, right? Because it seems that I'm assuming that under any condition, these two inputs are so close. But if these inputs are available to me from outside, surely I can go and apply whatever I want, right? I can apply 100 millivolts. I don't have to apply 10 millivolts. So then why am I saying that these inputs are always close to each other? That's something that we have to study as we go along, right? We'll see that this op amp is placed in what we call a feedback circuit, and the feedback circuit guarantees that V in 1 and V in 2 are close to each other. Now for now, we just focus on these two and not worry about any other little details, right? So we say, if I see a circuit that has an op-amp in it, I immediately make these assumptions. And then I proceed to analyze the circuit and see what it does. Now that you have an op-amp in there, what exactly is going on? Okay. All right. So with these two conditions, now we can go forward. So these conditions allow us to perform simpler analyses. So that's the key, right? The analysis that we have is simplified by these two assumptions. Actual op-amps don't really satisfy these. They may have some current at their inputs, and these two input voltages may not be exactly equal, but it's a very nice combination of these conditions that allows us to analyze circuits efficiently. All right, so let's go ahead and look at an example just to warm up and try to exercise some of these concepts. So I have an op-amp that I have bought. It has two inputs, V-in1 and V-in2, and I come along and I attach this V-in2 input, which we call the inverting input, to its output. So now I bring only one input here. I call it V-in. I don't have to call it V-in1 anymore. This is just V-in, right? And then this is V-out. So I hope this notation is not confusing. When we say this is V-in, what do we mean? We really mean that, yes, there's a ground here. Of course, the op-amp also has a ground connection. Let me do it like this so that it's not confusing. These lines go over each other. They're not connected to each other. So this input is really a voltage that is measured with respect to here. For example, it's just a voltage source like this, right? And then this output is also voltage that is measured from here to this ground, this general ground. But a lot of times we're too lazy, so we don't draw this, don't draw this. We just say V in here and V out here. Okay, so going back to the original problem. I have this op-amp. I connected its inverting input to its output. I have applied an input voltage to the non-inverting input, and I would like to find V out. How is V out related to V in? All right, so this is what we want to find. Okay, so our first reaction might be, wait a minute, we have an equivalent circuit for the op-amp. So why don't we plug in that equivalent circuit here and solve, right? KVLs and KCLs, right? Remember that we have an equivalent circuit for the op-amp from the previous page. So if I go back here, the equivalent circuit was this. Two inputs, a dependent source. So I say, in that triangle on the next page, I'm going to substitute this and then solve. We could do that, but let's not do that. Let's simplify things. Okay, well, the ideal op-amp ensures that V-in1 and V-in2 are close to each other. It means that this voltage and this voltage are close to each other. All right? Okay. So if I call this V-in, I'm allowed to call this also approximately V-in because they're always close to each other. So let's say, okay, this is V-in then, right, approximately. That was the condition that we had, right, for an ideal op-amp. All right, how much is V-out? Well, you can see that V-out is just shorted to this. So whatever you have here too. So V-out is just approximately equal to V-in. So weird but true. So all the circuit does is it generates an output voltage that is essentially a copy of the input voltage, right? We have an input voltage given by V-in. The output is also given by V-in. All right. So this is called a unity gain buffer. So that terminology is something that you should learn. A unity gain buffer. The term unity gain arises because V out is equal to the input. So if there's any gain to be had, it's just one. It takes the input, brings it to the output. And the term buffer is something related to the properties of the circuit that we will not talk about here. We talk about this in electronics design in the other courses that I have in my channel. All right. Now, of course, you might be asking, this really complex circuit generates an output which is equal to the input, right? So is it better than a piece of wire? You have a piece of wire and you give V in here and V out here. Isn't that the same as this, right? Here the output is equal to the input, here the output is equal to the input. So why do we bother with such complexity? So that's again something that you will learn in more advanced courses. No, these are not the same thing. This has some interesting properties that this one does not have. So, but this is beyond the scope of this course. You've got to go to the next electronics course to understand why this buffer is interesting and useful. Okay, so that was one little example to show you how we go about solving an op-amp circuit given these simple assumptions. The key point is that I did not have to draw the equivalent circuit inside this triangle to be able to find V out in terms of V in. I just said, well, the two inputs are approximately equal. This output happens to be equal to this input. Boom, we're done, right? Okay. Well, now we're going to go to a circuit that's more useful than this buffer, and that circuit is called a non-inverting amplifier. So this is a circuit that uses an op-amp and then performs amplification. So we're going to look at that and see. Today we'll start just familiarizing ourselves with the circuit, and next time we come back and analyze it more carefully. All right, so here's how it goes. I have an op-amp, and it's receiving an input. So again, we just call it V in, just like before. There's an output, V out, and we have a ground, right? Everything has a ground as a reference. So what we will do is we'll take the output voltage, pass it through a resistive divider, and then return the result to the inverting input of the op-amp. Here's how it goes. Here's my output. How do I divide it? I give it to two resistors, R1 and R2. We know that this voltage is less than this voltage, right? This is just divides it down. And then I take the signal and bring it back to the inverting input of the op-amp. All right. And our objective is to find V out in terms of V in, just the way we did it on top. Okay, so this notion that I take the output, do something with it, and bring it back to the input is extremely critical for op-amp circuits. Here, I took the output and I just brought it back to the input, right? Here, I took the output, divided it down, then brought back the result to this input. In both cases, what comes back connects to the inverting input, right? Here and here. And we will see why that's important. But in both cases, we took the output and brought back all of it, or brought back a fraction of it to the input. And we'll see that this exhibits some more interesting properties than that circuit. All right? Okay. So this is the circuit that we want to study. This is called a non-inverting amplifier. We have to see why we call it non-inverting, and we have to see why it's called an amplifier, right? Presumably, it amplifies, meaning the signal that goes in here comes out here. This signal is bigger than this signal. Here, the gain was 1. The output is equal to the input, so the gain, the voltage gain of this whole thing is 1. Here it might be different, so we have to see. Okay, so we'll come back to this next time and analyze it carefully. I will see you next time.